So welcome everyone. Thank you for joining today's session related to topic number 4-3, which is we're gonna focus on the live load distribution factor. As you remember from last time, we have been dealing with the loading, especially dead load and live load, and we got understanding on how to analyze the truck moving along the bridge or the longitudinal direction in terms of two methods. The first one was influence line method. The second one is moving load method. We were able to see if we have a truck that move over as simply supported span, or in some cases continuous spans, on how to get the reaction, maximum moment, and maximum shear. However, as you know, this analysis is done over longitudinal direction. However, the bridge itself has width, which this width can lead to several girders carrying the trucks. So we need to know now how those loads from the trucks will be distributed among the girders in the cross section. So we are at the end of bridge analysis topic, which hopefully you will be able to fully analyze the bridge for a given cross section. So here we will spend the first 25 slides just going as a refreshment and to recap on all related topics that we will be using to build on in this topic. So for example, you were able to lay out a cross section, right? So during your assignment, you were able to lay out how many steel girder you have, how many spacing, what is the overhang, what is the depth of your cross section for both steel girders and also box girders. For example, here in case of steel girder, one of the requirement is table 2.5.2.6.3-1, which give you the minimum depth, including deck thickness, that is required for case of simple spans or continuous spans based on material types and superstructure types. And this is just a refreshment for that. So for example, have a steel girder. As you can see here, we have limitations or actually minimum requirement for depth that you can get from the previous table. So in doing so, you can result in a cross section looks like that section. In this cross section, you can see the main elements are the steel girders, which carry mainly the loads. Correct. They are equally spacing in this problem, 4 as shown with 3 spacings. Okay. You also will have overhang, which typically 0.04 or 0.5 of the spacing. You may have also, you will have the slab or bridge deck, you will have haunch, and you'll also have a sidewalk, so pedestrian can walk on the bridge. You also have railing or barrier system, can be steel or concrete. And you have the distance out to out is a distance from the start of the concrete of the rail to the end of the rail from the other side. The distance which between the sidewalks can be called clear roadway width, and this where you are allowed to have trucks moving, right? Sometimes we even go extreme and we allow the truck to be placed 2 feet from the edge of the rail in case of the parking trucks over the sidewalk. But here, what you typically have, you will have two types of girders. One is exterior girders and one is interior girders. And during your homework number 3, you were clearly able to um, calculate the dead loads for exterior girder and interior girders. And now our focus is if we have a truck in this direction, moving along the bridge direction, how can I divide the load and distribute it between different girders? And this is what's called live load distribution factor. Continue with that, we know from previous what is DC, which is dead load of components. You need to know in this case we have a notation for DC1, which happen over the girder section, and DC2 will happen over the cross composite section. For example, you may have a steel girder, and after that you are placing the bridge deck. And this the weight of the bridge deck is actually a load on the steel girder. So this is can be counted as a DC1 deck loading. However, after curing of the deck with a steel girder and you have composite action using studs, you may have the barrier cast later. So in this case, the barrier is acting on a composite cross section. So this is a DC component that happen over the composite section. You also have DW, which is a weight dead load of wearing surfaces and utilities. You have live load, and you have impact dynamic load, which is what we call impact load dynamic load allowance, or IM, impact load. We also are familiar with the load combination. We spent so much time defining the different load combination and different load factors for dead load, live load, etc. We were able to get the loads from the unit, basically the unit weight of materials displayed in this table. We also dealt with the design trucks, and part of the design truck will be HS20 dash 44, which what we discussed so many times, that has to be a truck of front axle of 8 kips and rear axles of 32 kip, that actually attached with trailer of 32 kips as distance of between 14 and 30 feet, while the distance between the front and rear axle, the first two axles, are 14 feet constant. The width of between the wheels are 6 feet, as we discussed, and the total width of the truck is 10 feet, and the design lane is 12 feet, as we can see later on. This is a side view of the truck. As you can see, this is the width of the truck, and this is the distance between the wheels. You have 6 feet center to center, and you have 2 feet that start from the curb, counting left side. You also have design tandem, which is around 25 kips for each axle, spaced at 4 feet, representing military tank, and 4 feet width between the axle, and same cross section similar to the truck. You also have a convoy of trucks that represent the load, uniform load, so you have to have a combination now, and this load is 640 pounds per foot. It's uniform load per lane loaded. HL93 is combination of the line load, the dead load, sorry, the HS20, right, plus lane load, lane, or your tandem. Plus lane load. We also were exposed by load per state GOT. For example, here we are representing the load that has permit track for New Jersey DOT. And last lecture we covered this this permit track on influence line. We also have New Mexico, for example, as permit track B13. We also have California, which allow P5, P7, B9, B11, and B13 to drive over their highway bridge. We also defined what's called dynamic load allowance IM, which basically to translate or to take to account the impact of dynamic loading of speed of trucks on your structure. So most likely you use 33% for all other limit states. And for designing big joint, we use 75% to amplify the dynamic load allowance. Please make sure that you only count for IM in the HS20 and design tandem, but not in the design lane load. We have some rule we discussed is the design lane has to be 12 feet. Number of design lanes usually is a bridge width, which measured barrier to barrier. In this location, in this particular example, it's 44 feet, and you divide it by design lane, which is 12 feet. It gives you the number of lanes. You take the integer. If you have only two design lanes, you can go with design lane of 10 feet, but usually you go 12 feet design lane. You also need to take multiple present factor M. Multiple present factor M is very important to take to account probability of having trucks in same location, same time. So most likely you will have two trucks driving side by side. So this is 1% amplifiers, no amplification. But three trucks same time, same location is very hard to happen. So that's why we reduce it a little bit. So here is how we lay out the design lane. Let's say we have 44. We take 44, we divide over 12. We know it's going to be more than 3, but less than 4. More than 3, but less than 4 mean that you have 3 lane loading, or design lane. So you start from the edge of your barrier. You draw 12 feet area, which is going to be your lane number 1. You draw another one. This is design lane 2. And here you have design lane 3. And here you don't have enough 12 feet to have a fourth lane, but make sure that those lanes are also allowed to move laterally to maximize the bending moment and reaction and shear on your girders. So here is the final design of your lane load. First thing after you lay out your cross section, which is now you are very familiar with, is to count how many lane loads, and you start from the edge of the barrier, draw 12 feet, but place placeholder for a truck to be there in this lane load, another one, and another one, and you allow those design lane to float laterally, so they can start from here and end around there. You are required to calculate the distribution factor from live load to both interior and exterior girders. So this is actually in place in situ loading of bridges that happen sometimes, and this where you can see 3 trucks or loading trucks are occupying your bridge, and this is a case of 3 lane loaded. So in order to start layouting your truck, you know the truck in the cross section, it looks like you will have the cross section that we discussed on later on or earlier on in, sorry for the distances, the distance between the wheel are 6 feet, and they have 10 feet width total of the truck. And so the distance between here to the edge is 2 feet. From here to the edge is 2 feet. So what you will start with, you will have now, this is your first lane load we discussed. So you start 2 feet from the edge of the barrier, you put your first wheel, 6 feet away with the second wheel, and you know your truck ends with another 2 feet, which give you 12, or sorry, 10 feet width of truck, but the width of the lane is actually 12, correct? So after that, you add another truck. You start 2 feet from the edge of the first lane, 6 feet, 2 feet, and now you get your truck placed within the second lane load. As you can see here, you have axial load and wheel load line, wheel load line, and all the distance is 2, 6, and after that you have 2 and 2 and 2, which give you a distance also between the wheel at 6. So you can keep adding um, for the third lane. So if you keep adding from the beginning 2 feet, 6 feet, 2 feet, and gap of 2, and another 2, this will give you 6 feet. So basically, you can start layouting your loads at 6 feet intervals in the transfer direction. As you can see, it's clearly here, right? You have 6, you have 2 and 4, 6, you have 4, but you don't have another one here. You have 6. So you now are able to put 6 of axial loads, wheel loads on the cross section. And this is what we can discuss in details. So there are three methods. The first one called lever rule, second one called simplified equation by Ashton, third one is spatial analysis. So in Ashton LRFD, there is rule for called lever rule, and there is location where you should calculate using lever rule. Usually we use it for exterior girders. So let's say you have interior girders. This is part of your bridge. Let's say this is 3 girder bridge, only 9 feet spacing. What you need to do is you will create a hinge at every interior girder. You see here, this is your bridge, and you assume internal hinges in the interior girders that allow you to take the moment around the hinge from the left to get the reaction or the loads on the exterior girder. So let's say your truck was placed exactly where one axle of half the truck load, or one wheel line of the truck load is placed on top of the exterior girder, and you know the second distance between the wheels are 6 feet, so they are 3 feet from the interior and 6 feet from the exterior. Assuming that you have hinge here, you can assume that this is like simply supported beam. Take the moment around the hinge to get reaction in girder 1. So to take the reaction on girder 1, you can say 0.5 P times 9 feet plus another 0.5 p right here times 3 distance to this hinge feet equal RG1 times 9. If you rearrange it, you will see that RG1 would be 0.5p, is if you take 0.5p as common factor, will be 9 over 9 over 9, which is 1, 3 over 9, which is 9 minus 6 over 9. It give you that 2/3 of the truckload is going to the exterior girder because you loaded half already of the axle going directly to this exterior girder. In order to get RG2, you take the moment around the other hinge. That will result on half P times 6 over 9, which is 9 minus 3 over 9. Will give you third of the load in this particular configuration. Third of the load will go to the interior, and 2/3 will go for exterior. Make sure that you didn't, in this case, you didn't add multiple present factor M. In this case, you are only loading one truck, so those factor has to be multiplied times 1.2, as we showed earlier. You also need to calculate something called the stiffness parameter kg. So basically, this is very important for later calculations. So the first method is lever rule. It's super easy. It assumes hinges at the interior girder, and you take the moment around the hinges to get the reaction on the exterior girder. However, in order to use the simplified equation that I'm going to show later on, you have to calculate what's so-called stiffness parameter Kg. You have a slab, you have a centroid of a slab, you have a steel girder, you have a centroid of a steel girder. You can get from a steel girder area, moment, and modulus of elasticity for steel. Or if it's pre-stressed girder, it's going to be modulus of elasticity of concrete pre-stressed girder. You know how to calculate that because we explained the inertia area in topic 4-1. The equation Kg is N, which is a modular ratio, which we're going to explain. It's a ratio between the modulus of elasticity of the girder to the modulus of elasticity of the deck. So the modulus of elasticity of the girder can be steel or concrete. The decks can be concrete in some examples. So if you take this ratio, okay, between the material modulus of elasticity of material of the girder or the beam and modulus of elasticity of material of the deck, and this is usually n, you have to take the integer number. So if it's 7.9, 0.4 or 0.8, you take it as 7. You have I, which is the inertia of a steel girder or girder in general. Area A, which is the area of the beam, which is all defined here, times EG square. EG square is the distance between centroid of the girder to the centroid of the deck. Okay, so this is between the CG of the beam to the CG of the deck. So you have all those parameters for your cross section. Once you lay out, you can calculate that. It's basically trying to smoosh the girder with all properties to go to be acting at the centroid of the deck. And this, we're gonna use it for later. So we also have one important terminology, which is called the DE distance, which is the distance between the center of the exterior girder to the first wheel. So the S is spacing between the girder. TS is slab thickness. So let's say you have another girder here. The spacing S is a spacing between the girders. And you have the TS is the thickness of the deck. DE is the distance between axle load at the interior and the exterior girder if the axle is over the curb passing the exterior girder. So if the axle is in the other side of the girder, the distance DE is the distance between the girder centroid, vertical centroid, and the axle, and the span length L. So we need all those parameters from kg from previous slide. We need spacing between the girders, we need the slab thickness, we need the length, we need the DE in order to calculate live load distribution factor using simplified equations. So in order to, let me get the pointer here. In order to use the simplified equation, there is this table 46.2.1-1.1. It gives you a notation or symbols for each type of bridge you have. So, for example, if you have steel beams that carry concrete deck, cast in place concrete slab, precast concrete slab, or steel grid or glued panel wood on a steel beam, this will be your configuration A. And if you have, for example, cast in place concrete T-beam, which where mean that the bridge deck and the beam are cast monolithically. And if you have also precast concrete channel with shear keys, that will give you the cross section that you are interested in. We actually, in this class, I think we covered both cast in place box girder and we cover steel beam and we will cover precast concrete girder. So the symbol for that is A, F, and K. You can see in K, precast concrete, I or pop T sections. In top of it is cast in place concrete or precast concrete, which is bridge deck. So you need to know that which system you have, A, B, C, D, whatever, but most likely to be A or K. And in order to calculate your live load distribution factor, you have to go to another tables, and the tables have clearly saying what you are looking for. Live load distribution factor for moment on interior girders. Table 4.6.2.2.b-1. So if you want to calculate, if you have a girder, set of girders, and you want to calculate how much of live load will go for interior girders, when you calculate the moment, this is the table they are using. The table actually give you the applicability of the cross section. So section A and section K is under this row, and you have to use it. You have range of applicability. The span spacing between the girder has to be between 3.5 to 16 feet in order to be applicable. Thickness of this bridge deck should be between 4.5 and 12 inches. The span length should be between 20 feet to 240 feet. You have to have 4 or more girders in your cross section, and kg, the value that we calculated the stiffness parameter, has to be more than 10,000 and less than 7 million. Then, if you have to design for one design lane load, you assume just this bridge will have one design lane load out of the 3, for example, that you have. You have to try that and use this equation, which is 0.06 plus S spacing over 14 to the power of negative to the power of 0.4, S, which is spacing over the span length, to the power of 0.03 times kg stiffness parameter over 12 L spacing T cube all to the power 0.01. Make sure that you have the spacing in feet, okay? The span in feet, the spacing in feet, span in feet, thickness in inch, and kg in whatever equation that you will have in inches. For two or more design lanes, you will use this equation. So the factors 14 changed to 9.5, the power changed from 0.4 to 0.6, here the power changed from 0.3 to 0.2, and the constant changed from 0.06 to 0.075. And we will go through examples and we will clarify that. This only to calculate moment for interior beams. For exterior beams, if you have one lane load, again, applicability is A and K, which is our cases, pre-stressed concrete girder or steel girders. If one lane load, use river rule, or if you are actually two or more lane, in this case, you calculate what's so called G, which is a for exterior girder, live load distribution for exterior girder, you multiply G from interior girder, you calculate previously, times E, which is E equal 0.077 plus D over 9.1, when D is the distance between the exterior girder to the first axle of the truck. And if you have only number 3 girders in your cross section, you use the lesser of that and lever load. Okay. For skewed bridge support, you will have to calculate this parameter, which is C1, which is also a function of kg and a spacing between the girder and the length of a span. And the factor will be 1 minus C1 to the tans theta to the power 1.5. And theta is the skew angle. C1 is this term. Make sure that if theta is less than 30, you don't have correction. If it's more than 60, use a maximum correction of theta equals 60. Also, have table to calculate the shear, a distribution of live load for shear interior. Very simple equation. One lane loaded, use 0.36 plus spacing over 25. Two or more design lane loaded, use 0.2 plus S over 12 minus S over 35 to the power of 2. Or if you have, and the applicability, as you can see here, similar, 3.5 to 16 feet spacing between girders, 20 to 24 feet span length, 4.5 to 12 inches thickness of your girder. And if you have 4 or more girders. If you have 3 girders, you always gonna use lever rule. If you have to calculate it for exterior girder, one loaded, you're gonna use lever rule. 2 or more, you're gonna use the E equation, which is in this case 0.6 plus D over 10 to multiply time the exterior girder that you got from the previous slide. Or lever rule if you have more than this, only 3 girders. And there's a skew factor for that too. In your project, your skew is no more than 20 theta. So I don't think it will be problem for the moment, but you have to apply it for shear because applicability is between 0 and 60. So you can do that also using finite element analysis, but some actually software give you the live load distribution factor based on Ash. So let's go and have an exact like some assumption in order to be able to use this table, you assume the width of the deck is constant through the bridge, unless otherwise specify the number of beams is not less than 4. And if it's 3, actually use the specific equation for 3. Beams are parallel and approximately the same stiffness, so the beams has to be in parallel. There is no in the longitudinal direction, there is no like beam moving like this, right? You have like beam with varying spacing, and also the stiffness should be assumed approximately the same. Unless otherwise specified, the roadway part of the overhang DE does not exceed 3 feet, which is rarely can happen. Curvature in plane is less than specified in Article 46124. This is for bridge curvature. Cross section is constant across of the is constant with one of the cross section in the table. Remember the annotation A, B, C, D, and K, etc. It has to be from one of those cross sections. Now, there is one flow chart that we developed here in order to help you to see which method you're going to use. If you calculate for moment or shear, you have to calculate moment for interior or exterior. For interior, you only use method 2, which is the ASHTO table, LRFD. If you have exterior, you use method 1, which is lever rule or the table, or method 3, which is called special method, which we're gonna touch base at the end of this. And in shear, you have interior and exterior, okay? So we have the first method is lever rule, second method is simplify the equation, third method is special analysis. The length L is the span length, and there is also a table for it that tell you what is actually L. In positive moment, the length of the span for which moment is being calculated. For negative moments are the average length between the two adjacent spans. So for example, if we have two span bridge, if you calculate distribution factor for positive moments, it's going to be this way, right? You take this span as your L1, but if you take it for, sorry for the wrong that, for negative moment, you have to take the average of the span 1 and span 2. So we know from the lever rule that we discussed earlier that let's say you have uh, 3 girders or whatever number of girders you want to calculate for exterior only. What you can do, you can say, I can actually load the first truck here in this example, and also this truck will, since the wheel load line here, and this one is between the two girders, so this truck will distribute between the exterior and the first interior. And this could be the case only, no other trucks. And there is also going to be a case where you have 2 trucks side by side, and the second truck, because of the geometry, is going to distribute between the exterior and also interior. So we have 2 cases. The first case, A, when you have only one lane loaded. If you have only one lane loaded, you can see here, this can be considered half the load, and this is another half of the load. So you assume hinge at the first interior, and you calculate your load. In the moment here, the spacing is 16 feet, even if it violates the maximum 15 that we mentioned earlier. The reaction at the exterior girder will be R times 16, gonna be equal. Remember, we're only dealing with the first load loaded, which you should not consider this one in this case. So the first distance will be the distance between this load and the hinge. And if you can add 2 plus 6 plus 2 plus 4 plus 6 will give you almost, I believe, 20 feet, because 3 times 6 plus 2. So it's half the load P. And the second wheel line will be the other half P times 14, which is 2 plus 6, 8 plus 6, 40. If you solve for R, your R will be 1.625. So actually, because we have the truck overhanging from the girder, it's actually overloading the girder. Okay. You also have to, in this case, because you have only one truck, you have multiple present factor of 1.2, you have to multiply. So that this truck, this actually exterior girder will see 1.275 P. So amplification of the truckload by more than 127%. So in the case of two lane loaded, so you have now the two trucks, what you need to do the same. Now you have additional 2-point loads. So what you need to do is you have the first equation that we calculated before, right? From one lane loaded. You're going to add half times P times 8 because it's 2 plus 6, and another half times P times 2P, and this will result in 1.375. The multi-present factor for a two-lane loaded is actually 1. So you will be ending as two loaded will give you 1.375, while I think one loaded give you 1.275. So two loaded in this problem is actually more critical. So in order to calculate the simplified method, we came up with this example here. If you can see, we have four girders spaced at 12 feet centered with 3.5 bridge overhang, 3.5 feet. The distance out to out is 43. The roadway width is 40 feet, so inner is 40 feet. The first thing you need to calculate, you have 40 feet, you have the design lane width is 12, so now you have 3 lanes, right? Maximum 3 lanes. Thickness of the slab is 3.5. TS is important, you need TS, including half-inch for integral weighing surfaces. Concrete compressive strength is 4 KSI. Area of the cross section is 27.25. The greater cross section, and the inertia is 62,658. Calculate using the Ashto LRD, the live load distribution factor. So the first parameter that we need to calculate is kg. Kg is the equation is here. If you still remember, kg is n times I plus a e to the power ag to the power 2. The inertia is given from the previous slide. The area is also given. We need n, modular ratio, and we need the E value. So the modular ratio, you can calculate it based on the ratio between the steel, modulus of elasticity of steel and concrete. And for concrete, you can take it from the equation that is by Ashton. So the modular ratio in this case will be almost 8. In order to calculate EG is a centroid of the slab to centroid of the cross section. You can see here there is this 3.5, which is from the bottom of the web to the bottom of the slab. So in order to do so, we need that, and there is also a distance between top of this top flange to centroid of the girder, this distance were given to be 39.63, which is similar to what you calculate actually in homework number 3, right? So this distance here, measured from the top of the girder to the centroid of the cross section, you have 4.5, which is the thickness of the deck over 2 to give the centroid. Remember, it was 9.5, but half of this was artificial, not structural, for overlays. You also have the distance from the bottom of top flange to the bottom of this concrete, that's 3.5. So now you are actually counting the thickness of the top flange twice. You have to multiply, subtract one of them. So the distance E is 46.63. Now, assuming that you already calculated the kg value, which is became 1.81 to 10 to the power 9, we need to check the range. First of all, we need to calculate the bending moment for interior girder. Okay, let's say we start with interior girder bending moment. We go to the table. This is section A, type A. We calculate it for one design lane and one or two or more design lanes. We get this equation out. We check the range of applicability. The spacing was 12, so it's passing this applicability requirement. TS is 9, passing this applicability. L is, in this case, was 140. It's between 20 and 240. Number of girders was more than 4, and kg was less than 7 million, which is 1.81 million. So all you need to do is to write down this equation, put S here, 12 feet over 14, another 12 feet over L, which is 140. The first one is power 0.04, second one 0.03, kg 1.81 times 10 to the power 6 over 12. L is 140 in feet, TS in inches, all to power 0.1. I see give you a distribution factor of 0.528. If you repeat it again for uh, two or more lanes, you got 0.807 govern. Make sure in this table you already they counted for M, which is multiple present factors. So don't multiply, do not multiply times M. Okay, do not. If you want to calculate interior shear, you go for the table, you get extract the equation. For one design lane or two, it's only function of the span spacing. So you got super easy. S equal 12, we give you 0.84 lanes, or this equation 1.082 lanes on this governance. If you want to calculate the exterior, you have to calculate the bending moment. For one lane is lever rule, which if you calculate it and you add the multiple present factor, it could be 0.9 lanes. And if you calculate the E value here, your E, if you go back to the slide, it was around 2 feet given. That would make it 0.99. You multiply times 0.807, which is the interior girder moment distribution factor that you calculated earlier. It could be 0.799. In this case, the one lane load governors. In terms of exterior girder shear, you have also equation where you have a lever rule, we give you 0.9 lane as we did before, and you also calculate the E value, and now is 0.6 D over 10, give you 0.8. Your previous two or more loaded from interior was 1.82. You multiply times 0.8, it give you 0.856. Still the one lane load governed in the sheet. The last method we will discuss here today is method 3, only for exterior girder, which is basically this set of equations. So in order to know the set of equation, you have to for every truck, you will have a resultant called R1, R2, truck 1, truck 2, truck 3, and all the distances between this resultant and the bridge superstructure. So a lot of terminology to unfold this equation. So this is R is the distribution factor, the action on the exterior beams in terms of lanes. NL is number of loaded lanes under consideration. So if you consider one loaded, you put 1, 2 loaded 2, 3 lane loaded 3. E, this E is the eccentricity of the lane from the center of gravity of the pattern of the girders. We will explain that. So you have the girders, right? The girders are 4 or whatever numbers, right? There is center of gravity of them, maybe in the middle here. The lane is here. The two loads are left and right of the resultant. So the distance between the resultant to the centroid of the system of the girder or the pattern of girder is called E eccentricity. X is horizontal distance of the CG of the pattern of girder to each girder. So the distance here is X. This is X1, this is X2, etc. XE is X distance from center of gravity of pattern of girder to exterior girder, and NP is number of girders. Okay, so in this you have 4 girders. So for one lane loaded, 2 lane loaded, 3 don't loaded. N is 1, 2, and 3. Number of girders always constant 4. You have the part of the equation that give you is the distance between, if you have only one truck, you will multiply the distance between R1 and the centroid, which will come to be 15, 12 plus 3, 15, times the distance between the exterior to the centroid, which is 12 plus 6. Divided by every girder to the centroid is square. So girder 1 is 18 square, girder 2 is 6 square, 3 is 6 square. The distance here is 18 square. So if you add them up, you have 2 times 18 square and 6 times square times 2. Okay, this is always going to be constant value in all cases. In two lane loaded, now you need to add the other lane, the distance. This is going to be also fixed, XE. All you're going to do now is to add the second lane, which is similar to the first lane. The second lane distance now is 3 from the centroid of the second lane to the centroid of the girder. And the last one will be when you add the third lane is now is negative direction because it's the other side, so you put negative here, and you calculate, you get the factors, you multiply times multiple present factors here too, and you get the the live load distribution factor. In this case, 2 lane loaded were more critical. It's to summarize, In this special case, you have 1, 2, 3 loan loaded, and you can actually still summarize them for all cases for level load, the Ashton equation, and special method. Make sure also when you do the fatigue limit state, which you can discuss later, you will be doing only one lane loaded, and you have to divide by the multiple present factor from the table because it should not be including multiple present factor. I did my best to explain this. Please watch it before our session tomorrow. We will go through it again, and I'm pretty sure on following Monday I will be hopefully in person and maybe repeat part of this session topic 4-3 because very important topic. Unfortunately, I got sick over the weekend, so I was not able to be in person on this Monday, but hopefully back next Monday.